Hi, everybody. So in this particular video, I'm going to review eigenvalues and eigenvectors all over again real quickly to make sure you understand the basic process of how to find eigenvalues and eigenvectors. And then we'll also go and introduce a few more definitions here and there. And at the very end of the video, I'll go over two examples of finding the basis for each eigenspace for every eigenvalue for a single matrix. We'll have two matrices to work through, two examples. So we know that A times X equals lambda times X describes the eigenvalue and eigenvector. The eigenvalue is lambda, the eigenvector is X, assuming that X is non-trivial. In other words, not the zero vector. That can only be true if the matrix A minus lambda times I is not invertible, as you've seen before. That means then, so that the square matrix, if it's not invertible, then its determinant is 0. Now, this equation, the determinant of A minus lambda times I equals 0, has two new definitions that go with it. One is called the characteristic equation. That's the entire equation. And the other is the characteristic polynomial, because the left-hand side of the determinant of A minus lambda times I, that's actually a polynomial. It's a polynomial in I when you, it's a polynomial in lambda when you compute the entire determinant. It's actually a polynomial of nth degree if the matrix A is an n by n. So you have the characteristic polynomial, the left-hand side, the characteristic equation, the whole thing when it's equal to 0. So you'll hear me say a number of times, let's find the characteristic polynomial in order to set it equal to 0 to get the characteristic equation. We'll then solve that equation to get the eigenvalues. Okay, so then there's a number of other definitions we need. So just to remind you, for every single eigenvalue, there's something called an eigenspace, E sub lambda. It's just the null space of A minus lambda times I. We know the null space is non-trivial. We know there's at least one non-zero vector in it, because since we have an eigenvalue, there's at least one eigenvector. So that means then that the eigenspace is a non-trivial space. It's not the zero space. It's not the space that has only the zero vector in it. Now, with every eigenvalue, then we can associate two different terms. One's called the geometric multiplicity. That is just the dimension of the corresponding eigenspace. And since there's always in an eigenspace at least one non-zero vector, there's always at least one linearly independent vector in the space. And since the dimension is the maximum such number of linearly independent vectors in a space, then the dimension, the geometric multiplicity, is at least 1. Then you have what's next to it. You have another one connected to it called the algebraic multiplicity. In the characteristic polynomial, if you have an eigenvalue, then lambda minus that value would have to be a factor of that particular polynomial by the factor theorem from algebra you learned a long time ago. The corresponding factor, the maximum power on that factor, is called the multiplicity of the root. You've learned that a long time ago also from college algebra. We call it here the algebraic multiplicity of the eigenvalue. I think by example, you'll see how it works. Let's go over two matrices. So here's my first example. For this matrix, I'm going to find the characteristic polynomial first. So then I go and write down that determinant, and I have to smash it out. So I'll use a cofactor expansion on the last row. When you do so, there it is, and multiply it out to be this. You can then tell that there are two eigenvalues, 0 and 1. For each, I'll now find the corresponding eigenspace, which corresponds to a null space of A minus lambda times I. So let's find the basis then. Let's find a basis for E sub 0. E sub 0 is the null space of A minus 0 times I. So it's just the null space of A in this case. So to find a basis for that, if you remember how to find the basis for the null space, you take the coefficient matrix, you adjoin it with 0, you row reduce it. From that matrix, you can then determine how to take the system and put it back in terms of unknown variables. Some of these variables are leading variables. Some of these variables are free variables. You assign the free variables unknown parameters, and you solve the leading variables in terms of the free variables. You then are able to describe the solution vector in terms of free variables only. You then rip it apart to turn it into a linear combination of a free variable, a parameter, times a vector, plus a free variable, a parameter, times a vector, and so on. The vectors in that sum That's the basis for the null space. I did that for you here. I took the matrix, I row reduced it, and I just wrote down the basis for that particular null space. Since there's only one vector in the basis, the geometric multiplicity of 0 is 1. Since the factor x lambda minus 0, that's lambda. Since lambda has a power right here, see the power on it is 2 on that factor, that means its multiplicity as a 0 is called 2. It's just 2. We call that the algebraic multiplicity of that particular eigenvalue. I'll do this all over again now for the eigenvalue 1. So once again, I want to know the basis for E sub 1. That's a basis for the null space of A minus 1 times I. So here I go. I want to know a basis for the null space of A minus 1 times I. So I write down the corresponding coefficient matrix. I join it with the 0 vector to get the augmented matrix. I row reduce it. Once I get the row reduced echelon form, as you see right here, I then go and take the system, write it back in terms of variables, in terms of leading variables and free variables. To every free variable, I assign a parameter. I then take every single leading variable and solve it in terms of the free variables. And that allows me to write the solution in terms of free variables. I then rip it apart to get a linear combination of free variables times vectors. There's only one vector in this thing. And that's the vector 1, 0, 1. That's the basis of the corresponding null space of A minus I, which is the basis for the eigenspace E sub 1. Now, because there's only one vector in this basis, the geometric multiplicity is 1. Since the factor that goes with corresponds to the eigenvalue 1, that's lambda minus 1, that's actually right here. It's just written in the other order. So then the power on it right here is 1. So its algebraic multiplicity is just 1. So here for the eigenvalue 1, the algebraic and the multiplicity, the algebraic and the geometric multiplicities are equal. But for the same matrix, the eigenvalue 0, the algebraic multiplicity and the geometric multiplicity are not equal. But notice that in each case, the geometric multiplicity is less than or equal to the algebraic multiplicity. That's neat. Let's go ahead and try another one. So here's another matrix. Notice that this matrix is symmetric. So I picked this for a reason. It's symmetric. All right, so once again, I will find the eigenvalues. That will then determine the eigenspaces, and I'll find a basis for each eigenspace. So I first find the characteristic polynomial. That's this particular determinant. And this time I just wrote down the answer. You could then tell that 1 and 3 are your eigenvalues. For each eigenvalue, there's an eigenspace, which is non-trivial. It's not just a 0 vector, because there's at least one eigenvector for every eigenvalue, and the eigenvector is non-zero. So there's always a non-trivial eigenspace for any eigenvalue to look at. So let's look at the eigenvalue of 1. So E sub 1 is the null space of A minus 1 times I. So there you go. This is me just smashing it out. Once again, I have the matrix. This time, I'm not going to worry about the vector of zeros because we don't really need it, right? We know it's there, so I'm not going to waste the time actually putting it down. So the matrix 1, 1, 1, 1, 0, 0, 0, that's the matrix A, where you just subtract the identity matrix. That row reduces to the row reduced echelon form that you see here, or reduced row echelon form that you see here. That particular matrix, when you write it back in terms of a system where you have zeros on the right-hand side, that particular basis for the null space has 2 vectors in it. It's 1, negative 1, 0, and 0, 0, 1. So the geometric multiplicity of 1 is 2, because there's 2 vectors in the corresponding basis for the eigenspace. And the algebraic multiplicity is also 2, because for the eigenvalue of 1, you have this corresponding factor, and notice the power on it is 2. So here, the algebraic multiplicity and the geometric multiplicity are actually equal to each other. Let's go ahead and look at the next guy. So then looking at the next one for 3. So then the eigenspace E sub 3 is the basis of, I need a basis for the E sub 3. I need a basis then for the null space of A minus 3 times I. So once again, I'm just going to look at A minus 3 times A. I won't put down the column of zeros because when we do row operations, it doesn't do a damn thing anyway. So then I wrote down the corresponding matrix A minus 3 times I. I row reduced it to what you see here. That's the reduced row echelon form. From that, you can then read off the basis of the null space, and it winds up being 1, 1, 0. So here, the geometric multiplicity of E sub 3 is 1, and the algebraic multiplicity is also 1. In this matrix, for every eigenvalue, the geometric multiplicity was equal to the algebraic multiplicity. But you should notice in all my examples so far, in every single time, the geometric multiplicity was always less than or equal to the algebraic multiplicity. That will be important later, but not today. It's just something you should note. I think then that's enough for now, at least for this video. Now, most of the homework you have is just doing this over and over again. So then your homework is very computational. The rest of the videos, we bring up important ideas that we need for future classes. I think it's enough for this one.